All right, so we talked about one level of abstraction is you're just putting, bless you, gallium or boron, I'm sorry, arsenic or gallium or whatever, on silicon with some metal wires, and hey, you have a processor. Then we said, hey, look, you can also just think of it as a bunch of transistors with some metal wires. Hey, look, you have a processor. Next, the next level is called gates, where we're going to add some type of logic to it. So the simplest one is called an inverter. The idea is that if your input is a 0 bit, the output is 1. aka if you have no voltage coming in, it produces voltage coming out. On the other hand, if you have voltage in, it produces no voltage coming out. All right, inverter. What is this in C?
Exclamation point.
Yes,
Yeah.
it's the NOT. All right, seeing where this is starting to connect? How do we make a NOT inside of a circuit? Well, I'll give you this one. All right, well, that's not what you wanted. That's the picture for a NOT. The big symbol to understand is it's really this circle. Whenever you see a tiny circle like that, that means they're knotting it. And this is essentially how it looks. We're gonna add a little, well, you apply voltage. So you have ground, aka the sink. Input is whether it's on or off, and then you'll apply voltage. So let's look at what happens. If it's 0, aka this gate is not connected, then voltage flows through to out. One thing to keep in mind is that out is always going to have more resistance than going this way, and that's because out is going to have a bunch of things connected to it, so there's going to be resistance and whatnot. And electricity always wants to take the easiest flow or the simplest flow. So if there's a resistor versus non-resistance, it's going to go the non-resistive way. So just assume that O has some resistance over here. But right now, since this is not connected, even though there's some resistance, it's going to flow that direction. On the other hand, if you connect it, notice that there's no resistance to ground, a lot of resistance to out, and that'll make the voltage flow in this direction instead of the opposite, which will make O a 0. Okay. How are we doing? All right. Let me get some chalk, because this is going to be important. So we have our NOT. I guess I'll put it over here. Ooh, I have not used chalk in so long. How many transistors were there? Oh, I'm too even harder. How many transistors? 1. That's a resistor. That doesn't count. So there's 1 transistor. So I'm gonna say that the time delay for this is 1 for now. There's 1 transistor, so you know it has to be 1. Things are gonna get a little more complicated when you add more transistors, but we're gonna just stick with 1. And we'll say that, and the reason why we call it 1 is because when you push voltage down to connect it, electricity is not instantaneous. It takes time for the gate to connect and then for voltage to stop going in the O direction and actually flow in the other direction. There is a time delay for that. In general, it's considered just under the speed of light, which may seem instantaneous to us, but it does take time. And when you add a lot of little things together, you can get something big. So it's important we keep track of how long each thing takes. So a NOT takes 1, we're going to call it gate delay, is the term. All right. And we could go, one thing to keep in mind is when you see a bunch of these little guys, my wife calls them caterpillars. I think it's funny. The caterpillars usually have a bunch of circuits or gates, inside of them. This one just has a bunch of knots, just to show you what it looks like. But obviously, our chips are going to have more and more of these gates. I just wanted to give you a picture of what it looks like. And by the way, this is a breadboard in case you've never messed with one. And the cool thing about a breadboard was that each column is connected, so these are connected. It's not connected to this. This is another connection. All these are connected, so forth and so on, but they're not connected to each other. And so that helps you with wiring in order to move things from one to another. If you ever have a chance, if you get a chance to mess with breadboards, it is a lot of fun. Maybe we should do it in this class, but Not today. All right. So next comes NAND, negated AND. All right, it might be confusing why we're going straight to NAND and not to AND, but that's because NAND is actually a lot easier to draw or to use with transistors. So again, the round bullet is an AND, followed by a circle means it's nodding it. So the two inputs are first ANDed together and then nodded afterwards, and we call that a NAND, or negated AND. Okay, always great to write the truth table. How many of you, how many of y'all have not done truth tables? There we go. You haven't?
I've messed with them a little bit, but not a lot.
Okay, so most of y'all have looked at this. It's okay, you can tell me. I'll believe you. All right, good. So here's the different options for your inputs A and B, and Y is labeled as the output. AND of 0 and 0 is 0, nodding it as 1. AND of 0 and 1 is 0, nodding it as 1. AND of 1 and 0 is 0, nodding it as 1. The AND of 1 and 1 is 1, so you not 1 and you get 0. By the way, when you start working on a lot of these circuit diagrams, I highly recommend you always draw it, and if things are still too confusing, write out the truth table. By the way, one of those two things are going to help you. The diagram, I think, is the most helpful, but if you just can't get it, write out the truth table. It's going to take a long time, but the truth table is going to provide you the answer. It's just going to take a while. All right, so the NAND ends up looking something like this. So notice that the two transistors are in series. All right? So since they're in series, that means that in order for this wire to connect to ground, they both have to be connected, which means that electricity will only flow to ground if both A and B are off. And of course, if electricity flows to ground, then it will output a 0. So in other words, this transistor circuit is basically telling you you only go to ground if both are on. And so it's only 0 if both A and B are on. Otherwise, it's 1. Because if only B is on, it stops and can't get through A, so it goes through Y. And if A is on, well, it can't get to A because B isn't on. All right, how are we doing? Okay. Ooh, good question. What is the gate delay of this? 2 or is it 1?
1.
You're taking guesses, you gotta tell me.
No, I'm pretty confident in 1.
You're pretty confident in 1? Why do you think it's 1?
Because it's still one process, even though it's two, where is it? Can't remember the word, but I feel like it's 1.
Okay, so we got someone talking about their feelers.
Oh, stop.
Top sides, okay.
No, you're good. I can't explain it. I'm sorry. It's
All
my
right,
fault.
any other guesses?
Yeah.
Confidence? Ideas? That's
Yeah.
correct. You should.
Isn't it 2 because since series not parallel, it's got to go to 2 different things, right?
Well, can A and B both be applied at the same time?
No, wait, that's what I'm
Can both A and B be applied at the same time? Or are they applied at the same time, I should say?
saying.
Yes, they are applied at the same time. So the saturation of these two transistors are going to happen in parallel. Since they happen in parallel, the total gate delay is 1. Got it? Even though you use 2 transistors, the gate delay is 1 because they are happening, the saturation of them is happening in parallel. If, on the other hand, the output of A was going into B, then that would be series because this has to saturate before B can start saturating, and then that would be a series. But as both A and B can be applied at the same time, the total gate delay is 1. Are we okay? All right. All right, now we get to the fun part. And Oh wait. So and 0, the and of 0 and 0 is 0. The and of 0 and 1 is 0. The and of 1 and 0 is of course 0, and the and of 1 and 1 is 1. All right. Now let's see if this thing goes up. Please go up. Wow. This is terrible. Yeah. All right.
And now it'll never come back down.
Yeah, now it'll never come back down. All right, so of a NAND, this is so I didn't have to try to figure out how to draw this thing. All right, so that was a NAND. Now we want to do an AND. Oh, this is so much better. I don't have to think, I just write it. That was great. All right. Who wants to draw an AND? This is not correct. Spoiler alert.
Is it an and?
Yeah, we're drawing an AND. Turn off. Yeah. And okay, not bad. Who's got this? Oh, you're leaving. Nice. Well played, sir. Well played. Well played. All right. All right. Who can think of what an AND would look like? Let me help you out. Oh, we don't have an eraser? Oh, there. Oh, that's terrible. I do this because it's going to look like this, only a little different. Any guesses? Comments? Well, there's different ways to go about it. Let's do the easy way first. We already have a NAND, and we already have a NOT.
So we just add the not to the and.
Right, so we could do this. Right? Because you not the and, you not the not of the and, you get back the and. So luckily in circuit diagrams, not A equals A. So that would work. So you'd have this followed by, let's see, so that would have to go into the input. We'll do that. Actually, I like that. And that would go, what is that, into the input. Ooh. Anyone remember how the inverter was done? I don't know. Oh, thank you. Whew, that was close. Yeah, so it does go into here. And that goes to ground, right? Yep. And then, okay, good. Yes.
What's the triangle again?
That is an inverter. What's the gate delay here?
This one.
Why is it 2?
Because you have the, first you have the NAND going in parallel.
Yeah, so
So then the NOT happens after.
right. So,
You add the NAND and the NOT.
all right, is it very clear why the NAND is 1, but the AND is 2?
No.
No. So, do you understand, I guess, so we'll start with the NAND. So the NAND is just this part right here, right?
Okay.
So A and B get applied simultaneously, aka in parallel, which means that this transistor and that transistor are going to saturate to the correct value in 1 gate delay because they're both being applied at the same time. All right? All right. So since they're both being applied at the same time, then the flow will be correct in 1 gate delay because these both can saturate in 1. Now, in order for the inverter to saturate to the correct value, its input depends on the output of the NAND. So the NAND has to complete its saturation before the inverter can start moving towards the correct value. The inverter takes 1, it's 1 transistor, but it has to wait on the NAND, which takes 1. So it has to take 1 for this to complete, and since it's connected to the input here, it's waiting, and so it's going to take another 1 in order to move forward.
Okay.
Okay?
I mean, I still don't understand this whole thing in general, but I get that.
You get this?
Yeah.
Another way to look at this, and this will probably be easier, and this is why drawing the diagram is way better. This is 1 gate delay. This is 1 gate delay. He depends on the output of that, so you're doing 1 plus 1. You're gonna, when you start evaluating, you're gonna be looking here. I'm just writing it down here so you understand low level what's happening. How we do it. It needs like a blank. Does this have a blank out, or is it just? Nope. Okay. I guess we'll go to OR, and it'll pop up and it'll be funny. Oh, this stuff is messy. Look at that. Whew. All right. So the next one is an OR, which looks like a pointy bullet. And it has the situation looking like that. Oh, nice. Yeah, breaking chalk. Okay. All right, this one's going to be harder. Let me turn this off. Welcome back. Any ideas about how to do an OR?
A and B are both diodes, correct?
I'm sorry?
A and B are both separately diodes, correct?
No, they're input wires.
Input wires.
Input wires.
Well, judging from the output you're getting, they must be independent of each other.
Yes.
One wouldn't have to rely on the other for the current to flow, so.
Correct. Well, A and B are inputs. They're coming in. Like if you're ANDing 2 Boolean expressions, A is the first one, B is the second one. Okay, obviously this is not right. Right. So we want 0 and 0 to be false. Any ideas? Comments?
Well, would A and B not be in a series then?
So this picture may be messing you up because there are many different ways to do this.
Okay.
Which way? Give yourself a couple minutes, draw some out. I'm gonna let y'all think about it. Yeah, I'll give you some time. See if someone can come up with it. For these, it's really a lot easier if you start, these are your inputs and these are the outputs you want. How can we get to them? You got this? Nope, no.
Okay, I think I remember what. I think I remember what.
Alright. Wait, I need to.
There might be two different ways. I'm not sure.
Oh, there are many,
Well,
many different ways to do
I
it.
think what it is you.
Well, here, we got chalk. We got chalk
I
and an
don't know.
eraser.
I remember what the draw is.
Just draw it on the board. Just start. We'll all heckle you and help you out at the same time.
I know what it is. I just don't remember how it is. It'd be like two knots, a knot A, knot B, and then an and together.
All right. Well,
I don't remember.
well, I mean, that's one way to do it.
Yeah. You recording the chalkboard?
I'm pretty sure I am.
Which
Let me double check.
one is this is the NAND still, right?
That's the NAND. Yeah, I'm
What did I say
recording.
what the knot was? The knot was just.
It was basically the ground going over here instead of to A first.
Okay. So. Okay. So. These both need to be knotted. So. The ground goes to. Hold on. I'm getting myself confused. Right here. Would you want to knot both of these, right?
Okay, not the.
I'm trying to
You mean
think.
A and B or?
I want A knot and B knot, so they're both knotted before they go into the NAND gate. That's gonna get you the OR.
Oh, okay. Well, draw that up top. So
I'm just not sure how to draw them.
we'll worry about that later. You
Okay.
can draw if you're gonna do it the gateway, which is fine. That's one way to look at it.
Like, so this was what I was thinking.
That's the OR gate. So don't
yeah.
use an OR
No,
gate.
no,
of
I
course.
know. You mean to draw that. So A. Are we doing this for the knot or
Mm-hmm.
Okay.
Yep.
B? That's what I wanted to do. I did the truth table and I checked it, but
Okay.
that should.
So then let's see what we get. So if A is 0 and B is 0, then both zeros go into the NAND. Both of them go into the NAND as a 1, which will make it true, and then knotting that will make it false. So now the fruit. Well, what you do now? Let me draw this out for everyone.
Yeah.
So you drew this diagram. Thank you. So the thing to do now is to check each level of the truth table. The truth table has 4 options. As long as these inputs produce that output, it's an OR gate. All right, that's what the truth table is telling you. These are the only possible combinations. So let's start with the first one, right here. So if A is 0 and B is 0, when you knot that, you get 1 and 1, right? If the NAND, if you AND 1 and 1, you get 1, and then when you knot that, you get 0. Right? Right. So, is that correct? Yes. All right, let's try the next one. Was it A is 0, B is, okay. 0, 1, so we get 1 and 0. The NAND of 1 and 0 is, well, the AND is 0. Knotting that makes it a 1. Which is what we wanted. By the way, in case that wasn't clear. All right. To the next one, 1 and 0, the knot of 1, 0, the knot of 0, the NAND of 0 and 1, 1. Because the AND of 0, 1, 0, knotting it makes it a 1. And that's what we wanted. Okay, so now we have what? Both on, 1 and 1. Knot of 1 is 0, the knot of 1 is 0, the NAND of 0 and 0 is 1, right? Because the AND is 0, knotting it makes it 1. The output, we want it to be 1. Hey, we're done. This is perfectly fine to draw. You don't have to do all this. This is just to help us go from the physics to the diagram. when you're trying to help yourself draw these diagrams, I highly recommend you stick to this. You're gonna go nuts if you try and look at this. Look at this guy up here. Okay. What's the gate delay? Yes, it's 2. Why is it 2?
2 knots happen to like
In parallel.
basically.
Yeah. So the 2 knots happen in parallel. And then the NAND is waiting for the output of the 2 knots, so the NAND has to wait for the 2 knots to saturate before the NAND will give you the correct answer. So the answer, the gate delay here is 2. Okay, how are we doing? You all right? All right. Next comes XOR, is that right? All right. Here comes the fun one. By fun, I mean, yeah. I think we're done drawing transistors this way. All right. XOR. One or the other, but not both. I'll give you a couple of minutes on this one as well. This is definitely the hardest one. All right, online student, hopefully I can grab a USB extension cord and make this picture a little better next time. But it's not, it's
Anyway, you-
bolted to the ground. Yeah.
Well, I was gonna say to hit this.
Oh yeah, let's see if that helps you any. That's a little better, but I think over there we'll, yeah, because you can't, from the screen I can't read that, and not, it's like a giant fuzz. All right, anyone have an idea? Nope. This one's actually really hard. This one's hard. Okay. You got an idea? Go for it. Thank you.
Can I do this right?
Yeah, you can have A as many times as you want. Sure. All right. Okay. All right. Let's see what happened. By the way, just to fix this real quick. Right? That way we don't have to have A and B. By convention, you only have it once, but if you want to fan out, there's no problem doing that in circuit diagrams. All right, let's see what happens. So A is 0, B is 0, the NOT of A is 1, and the NOT of B is 1. 1 NAND 0 is, well, the AND is 0, dotting that makes it 1. And let's see what happens here. 0 and 0 and 1. The NAND of that is also 1. And now we're going to NAND the two 1s. So it's AND NOT, which makes this 0, right? Hey, all right, doing great so far. By the way, this whole process of writing what the values are on the diagram is going to be really, really helpful. Even when we start on our Verilog. You're doing Verilog, you can't figure it out, draw the diagram. Makes them 0, 1, right? All right. Well, that's still 1. The NOT is 0. So the NAND, what's the NAND of 1 and 1?
0.
Okay. What's the NAND of 0 and 0? 1. What is the NAND of 0, 1? All right. Okay. The NOT of 1 is 0. The NOT of 0 is 1. So the NAND of 0 and 0, AND of 0, 0, 0, nodding that is 1. The NAND of 1 and 1 is 0. The NAND of 1 and 0 is 1. All right, looking good. All right, so the NOT of 1 is still 0, that hasn't changed. The NOT of 1 is also 0, great. So the NAND of 0 and 1 is 1. All right, wait, NAND of, yeah. And the NAND of 0 and 1 is 1, and then what's the NAND of 1 and 1? 0. All right. Ooh, told you this one was harder. What's the gauge delay here? 3.
Does the NOTs have a parallel?
We have 2.
And then the two NANDs have a parallel on the last.
So each I know that each knot, even though there's only one for each one, is actually waiting for the knot, so that counts as one going through each.
So sometimes, so we're getting different numbers. We got 4, we got 3, we got 2. All right. Okay. Sometimes it helps to look at this backwards, especially since there's only one output. How long does this thing take to saturate? 1. But it's relying on 2 inputs, right? Well, we got this NAND and that NAND. How long does these take? 1 and 1. What are these guys relying on? Well, he's the inverter, so this inverter is still 1 and that inverter is still 1. What is the longest path? Because you could go 1, 1, and that would just be 2, but there's the inverter here, which takes 1, 2, 3 in order to get through. And you always have to go with the longest path, because it could be a situation where that is the thing that changes everything. So, in this case, we go with 3. All right. Some of y'all are thinking, how could you possibly come up with this? You use the force. I don't know. You gotta figure it out. You put some things together, you figure it out, and eventually come up with it. You are gonna have a couple assignments asking about this just to get you to think about it, but that is not the majority of this course, at least for now. But the idea of how to package together circuits from your tools that you have is going to pop up. So definitely get used to it. It's just not necessarily going to be like this all the time. Okay, how are we doing? You got this?
A lot of it's flying above my head, but.
Well, at least I recorded it, hopefully. Draw the diagram. Always draw the diagram. You're stuck, draw the diagram. Still stuck, draw the truth table. Start throwing numbers through. Something will pop up.
Well, so far, this is probably the only thing that hasn't completely shot over my head so far.
Okay, great.